Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're going to talk about carbon nanotubes. So let's dive right into it. Well, first we have to understand what the heck we are talking about. We are talking about a tube that is made out of carbon atom. It's in the name, carbon nanotube. Now this is a tube. Now be mindful, tubes we are made out of metal, wood or whatever have you, but generally they are multiple atom things or sometimes multiple molecule things. But this time what we are talking about is a very specific crystal structure which is made out of single atom thickness. Be mindful, it's basically graphene rolled into self. That's all we are talking about. We are talking about tube which could have diameter of varying difference. It could go as high as 100 nanometer to as small as 0.5 nanometers or even smaller, but the thickness will always remain one atom, one carbon atom thick. That is the critical aspect of here, and it's a pure crystal structure. What does that mean? That means there is no other things mixed into it. There are crystal structure, crystal lattice, like metal alloys. That's what we are talking about. We're generally mixing a bronze or tin or something like that with something else to get different properties. Here we are getting raw properties of carbon, so it's almost like diamond. It is diamond in one way if you look at it. Now here's the reason why we are so fascinated by this is because it's one of the strongest material known to man. Now what does that mean? That means this puppy can be harder than diamond while stronger than steel while being lighter than that. Basically carbon nanotube could be so light that if you have a thread out there, you let it will slowly fall, because again it's that light. It's literally lighter than air, so to say. So that's what we are talking about here. Carbon nanotube is a graphene sheet rolled up, one atom thick. Now scale of this is kind of critical to understand here, because it's a very high aspect ratio material, because there are many things, like even let's say spider silk. If you think about that, you may think okay, it's a continuous silk, but if you zoom in, like you really go into electron microscope and start to see that, you will see there are multiple linkages. Like there are elements that are bounded like this. There are linkages here, so that's not a continuous structure. Everything in this world has like that. Basically even a thread, it has multiple small linkages and all of them combining into making into a big thing. This puppy kind of bypasses that law. It basically has very high aspect ratio, and I mean on an atomic structure, as in like crystal lattice wise, it does not have a limitation. So you can make it like a thread on a molecular level. Basically it's not a multiple small thread which are bound together by friction. This is an inherent length. Basically if you want to pull it apart, you are directly fighting chemical force, not friction force. So that is awesome in the authors. And this puppy can be very small. Like this is a human hair and this is a normal carbon fiber thread. Now invert the image one more time. Basically this make this carbon fiber strand into this human hair. This would be carbon nanotube. Carbon nanotube is idiotically small. Again, it's a single atom kind of structure. It's not very big. Now you can make it big as like 100 nanometer big. At that point you will barely see it, but you get the point. It's very small. Now what about the, I'm talking about the diameter, like you can control it. What about the length? That's the interesting one. That's why the very high aspect ratio is such a amusing part. You can make them like 10 nanometer, you can make them into 10 millimeter, you can make them into 10 kilometers or thousands of kilometers. There is no inherent physics limitation where it's like no, you shall not cross that. Like it happens with almost every chemical structure or molecular bond. When you start to make them very big, they start to break apart on their own. This puppy does not do that. That's another aspect of it. That's why we are so interesting about it. Now the thickness, basically how big the diameter of that pipe is controllable. So if you, let's say you want to make a semiconductor, it's like bro, I need big fat pipes because I have to dope it with silicon or something like that. Let's say you want to put something into that hollow pipe. You're like okay, we can grow it. Be mindful of, we do not manufacture it, we grow it. We basically have a chemical deposition structure and we're like okay, if we grow it on top of titanium, we're gonna get like fat pipes. If we grow it on copper, we're gonna get very long one but very thin one. So it's up to you. We control the growth aspect. So right now we have a good control where it's like okay, you want a fat one or you want a very thin one, we can control that aspect. And length one, that's the tricky part right now. Diameter, we got this. So that's the scale we are talking about. We are talking about a true nanotechnology. Is the same nanotechnology as used in basically your silicon wafer technology, much smaller. Now we are talking about crystal structure, lattice, chemical, chemistry. What the hell all does that mean? That simply means give a damn about angle. Everything about carbon nanotube depends on its angle. The reason why people were so excited about carbon nanotube in early 2010s is simply because it was a magic material. It has 300 gigapascal strength. What does that mean? That means this puppy was strong enough that you can make a space elevator on this cable. It was god tier level strength while it being lighter. So how the heck we reached there? Well, we did not reach there. We simply did the mathematical calculation based on the chemical bonding. So because it's an atomic structure, lattice is controllable, you can control its property. Now, do we do that? Well, yes, that's how we make silicon system. That's how we can say this silicon, hey bro, this silicon, you're supposed to be a semiconductor. This silicon, you're supposed to be a conductor. This silicon, you're supposed to be off. So we can control that on a molecular level. And same another things we do with plastic also. Plastic, we dope it with something else. As like, bro, on a chemical level, you should be transparent. On a chemical level, you should have black color. Like on a chemical level, we are doing that. So we are experienced with nanotechnology. So this puppy is next evolution of that. Now, why would you like to control the properties? Well, let's say you want semiconductor, you're gonna make zigzag. What if you want a strong, space elevator cable? You're gonna use armchair. Like, what the hell? They are same carbon nanotube. What the hell is happening here? All you are changing is the angle. So basically, if you take because it's a hexagon, it's not an octagon. It has like short side and long side. So if all the long side is basically perpendicular to the length, you're gonna get armchair. If basically you take an angle, you're gonna tuk 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 tuk, you're doing zigzag structure. If you are like tween 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 tween, that's armchair. Now armchair is the stronger one, zigzag is a semiconductor one. But here's the reality: when you grow it, quote unquote grow it, you don't control it. Like, you want to control it, but physics, chemistry, quantum physics, they are like, no, you shall not have complete control. So outcome is generally chiral structures which are like neither, basically they are stuck between 290 degrees. They are not awesome. So we can control the property basically same way we control the properties of basically silicon. We control the properties of this also. So you can have complete metallic behavior. Basically at that point it's like, oh, it's better than copper because this has what we call electron ballistic trajectory. What does that mean? Best way I can explain that is basically you put 100 electrons there, it sends 100 out there. Inherently it's a superconductor, so to say. So if, and many people are working on it, basically this is the closest candidate we have at this point in time that can make a true superconductor at room temperature. So it's quite amazing if it works out. Right now we have not made long enough and not enough people have experimented on this, so but it is feasible, let's just put it that way. Now semiconductor, a lot of people are interested about this because the electron efficiency, even if it's not a superconductor, it does have efficiency. What does that translate to? That translates to our silicon industry has reached a maximum limit. We cannot make it any smaller, we cannot make it any faster. That's why, like, if you are old enough where you are like computers, oh, 50 megahertz, we went from 50 to 500 to 1 gigahertz to 2 gigahertz 3, like these things happen so drastically fast, like whoosh. And then we got a ceiling where we are no longer even touching 5 gigahertz. Not even 4 gigahertz is a normal thing. Like 3 gigahertz, like we have maxed out there. Why? Because silicon does not like higher frequency than that. Like it starts to generate way too much heat. So people are like gallium nitride. They want to switch to up to that. Again, we have some issues there, but that should allow us to go to as 25 gigahertz, so to say. This puppy, 100 gigahertz. Let that sink in. This puppy can literally turbocharge our current existing structures of semiconductor and take it to 100 gigahertz, like YOLO fast. So that's why we want to control the actual real world structure of this. But be mindful, the strength varies a lot. This is when people were like doing the armchair mathematics, there's like 300 gigapascal. When they actually did the testing, it's nowhere near, it's like barely 30. So what happened? Reality happened. In reality, it's very difficult to get a proper armchair, very difficult to get proper zigzag. So generally we end up with chiral system, and not to mention, because we are growing it, we are not manufacturing it, we end up with defects where basically there are holes in this structure. Outcome breaks from that position. So it's very big. Now be mindful, even in the weakest state, basically the lowest we have gotten is still in gigapascal. So what does that mean? That means you can make a Kevlar waste out of this puppy, it would be hundreds of times stronger. It's still better than that, but it's no longer the magical material that was promised. It's like, the prince that was promised is no longer the truth here. So be mindful, angle is the key. Understand the angle, you will understand the property. Generally you want either zigzag or armchair. Reality will bit slap you and put you into chiral. So deal with it. That's the angle. Now there is another aspect. It's a tube, it's a hollow tube. What if you put another tube inside that tube? So we have single, generally when you grow something normal, simple, something you can afford, is generally single tube. It's most the common one. Most of the research are done on that. However, if you know how to do it, you can have tube inside a tube inside a tube. So far people have reached from 3 to 5. 3 is quite common, you can get 3 tubes. And this puppy was very fat. At that point, the third diameter would be around 100 nanometers. So it's still an atomic structure. It's not like a huge thing, still an atomic structure, but damn strong. At this point in time, it will not behave like a semiconductor, it will behave like a metal. It's completely metallic system. Properties wise, it is metallic. Strength wise, god tier awesome. So that's the generally what we do. But given the fact that we have a hard time getting a single one which is like perfectly aligned, we have another like whole another level of difficulty trying to get this puppy properly behaving. There are some thought processes that they want to use this as a syringe, but again you have to find a molecule that is small enough that can actually travel in this. But you get the point, there is a lot of potential in this if you can put tube inside a tube inside a tube. So a lot of focus is also placed into this exact behavior of it. Now one thing you have to understand, there is a lot of dial down to carbon nanotube. Like we used to hear carbon nanotube, like for example Black carbon nanotube paint, 100% absorption of light. Now it was mind-bogglingly awesome, but yes, still they removed it. The company that made the Black, they are no longer using carbon nanotube. Why? It's hazardous to us. Now carbon nanotube is very small, like it's very small, but it's also very long. Here's the deal: on a very small scale, this behaves the properties of asbestos. Basically, asbestos has, like, if you zoom in, like on an electron microscope, you will see long shards, and that shards have like exact same properties of carbon nanotubes. So what does that mean? That inherently means our lung has a cleaning architecture. That's why you survive. That's why dust does not end up killing you. We have an architecture that goes there and it's like, I got this, there is dust party, it collapses on it, creates a sphere, your blood system pures it out. It's like, we got this cleaning system, awesome. When you have long stranded thread, it gets stuck, it cannot be clogged up. Basically it creates a wound in your lung which cannot be healed, and this will remain as long as you live, or the most likely outcome, this will cause cancer and you dead. So this is literally like how asbestos was there, like, you know, asbestos, magical thing, magical insulator, we put it everywhere and we have to remove it from everywhere because it was causing severe health hazard. So same thing has been realized with carbon nanotube, and given the fact that carbon nanotube literally has the probability to go through your skin, like if there is, let's say, because again we do not have the technology to make one continuous thread, and you have let's say grown which are like few micrometer and they are spread in there is a risk that can directly go into your bloodstream. That would be bad. So carbon nanotube is too small and too damn long, so it's a very difficult for human lungs cleaning capacity to clean it. It can't clean it. So at this point in time, it's classified as hazardous. Now again, it's not toxic, it's not radioactive, but it is hazardous. Basically, you have to know what you're doing with and be mindful. Exposed to this, you cannot heal. Like, it's not like wood dust or, like, you know, sawdust. It's very dangerous. So it is something that is, a lot of people around in 2008 started to look into. They're like, bro, we did this mistake with asbestos, let's be cautious here. And not to mention, many companies have already removed carbon nanotube from Black. Now be mindful, this is one of the worst example of scientific journalism, the hype created around this. The selling point, it will change the world, superconductor at room temperature, which nobody has done so far, but because it has electron ballistic trajectory, people are like, yeah, you should do that. I'm like, let somebody figure out, like, it has 300 gigapascal, let somebody actually test it. The moment somebody actually tests it, is like, yeah, 30. Now again, be mindful, it's still multiple times better than anything we have, but not space elevator. So because of so much rush put into it around 2008 to 2010, it's like, god damn, like I got so much requests with carbon nanotube. It's nowhere near where people expect it to, because most people do not have the context of it. Like, Einstein came up with the idea of laser, then some engineer around 30 to 40 years later came up with the actual laser made out of microwave, and then 40 years from that somebody actually came up with the infrared laser, which we use in things like CD, DVD, Blu-ray and things of that nature. So it takes time. It's normal for scientific things to take time. The things that we are seeing today, even a semiconductor industry, the foundation has been laid down years ago. That's normal. It's not like, oh, somebody made it in the lab and tada. That's not how it happens. Like, it takes years, decades, or sometimes a whole goddamn century. Like, we had plastic for 100 years. It took time for it to, like, you know, become the as commonly used as it is. It takes time. So the selling point of carbon nanotube, it's magic and it's here. It's almost like hyperloop. So, but reality was, it's not that. We can make them. That's absolutely true. No, if you are dealing with scientists, they know how to build this. That's absolutely true. We have made it. But here's the deal, we can just make composite at this point in time. What does that mean? That simply means you can have these strands, we try to make them as long as possible, and then we put them in tennis rackets. So we are kind of reinforcing it. Basically, how you can take concrete and put fibers into that to improve its behavior pattern. Same, we can do this with it. Like, it's compositing material. Basically, you are making an alloy. So we have been doing that. There are products that you can buy which has true carbon nanotube into it. It's absolutely real, undeniably so. However, it's just that composite. We are not like carbon masters of carbon nanotube. We cannot, like, the world record is freaking half meter. So we are not a place where we can make threads of that. Now the moment we reach the threading stage, then it's a different thing. At that point you can be damn sure, because it's the strength level. It's not something that, let's say you make a car axle out of that, it's just magically gonna turn into dust and cause hazardous. That's not gonna happen. But again, we are not there where you can just buy, oh, carbon nanotube thread spool. If we reach that point, then it will be like God. At that point, tanks will be made out of that. At that point, body armor would be made out of that. Right now, we are not there. Now, are we better than what we have been before? Absolutely. Compositing it does yield some advantage. US military is actually spending billions of dollars in this. It's a true advantage, but it's not that much. Like, it's not like, whoa, our armor was like, 10%, now we are 90%. No, it's like our armor was 10%, now it's 12% without increasing too much weight. So awesome. Definitely better than zero, but not that magic. It's no longer magic. Just relax. I would urge you all to just relax. Relax, because again, it's the job of a news industry to troll you, so don't get trolled. So once we reach that point where you don't need electron freaking microscope to see it, yeah, at that point we are starting to manufacture it. We are very far away from that, very far away. So this was my presentation on carbon nanotubes. I hope you liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me a disappointment. Please leave a comment because I try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.